Congratulations on winning a Bell Award recently.
Thank you so much. Come in. Okay, so this is our office. Okay, this is my teammate Alia. Another one is here at her department. This is Farah, busy doing her work. And another one, Ain, where are you?
Yeah.
Okay, let's look at her. And this is one of my colleagues also, Ain.
Hi. So, can you tell us about your project?
Okay, so our project is basically about vibration of couple system. Since this project is about spring system, so it involves Hooke's law, Newton's second law of motion.
What is that?
Oh, okay. Hooke's law is a force needed to extend or compress a spring to a certain distance, and it has a formula of F equals to negative kx. I'm sure you know what is Newton's second law of motion, right?
Yes, F equal to ma, right?
Ooh, wow! Isaac Newton detected. But wait, I'm not done yet. Couple system equation is an equation formed of two differential equation with two dependent variable and an independent variable. Besides, normal mode vibration is also applied in our study. Normal mode vibration are free vibration that depends on mass and stiffness of the system. Apart from that, our system also involves 2 degree of freedom system, which means here, minimum of 2 coordinates are needed to represent the motion of the system. Therefore, 2 system of equation is needed to solve the system.
Oh, interesting.
Thank you.
What is the purpose of this project?
We conducted this project to understand the behavior of vibration of couple system. In order to do so, we perform Laplace transform on the system. And from there, we obtain the vertical displacement of the spring. That's how this project win an award.
Wow, that's so cool.
Thank you. Oops, I'm sorry, I need to take this call. Bye.
Hey, what you doing?
Hi, nothing. Just compiling my work.
Is that the project that won a Bell Award?
Oh, of course. Let me show you how our project looks like. Okay, so if you look at this model, 2 masses are attached at the end of 3 springs. So these 3 K's here represent the spring constant. By using Newton's second law, we got this equation, as you can see. So as you can see here, we need this initial condition to solve the Laplace transform. From this equation, we will obtain vertical displacement, which is xt and yt.
Manual solution to solve this system. So we have 2 linear differential equations. The first one is m1 s double prime equal to negative k1x plus k2 multiplied with y minus x with initial condition x at 0 equal to 0, x prime 0 equal to negative 1. For the second equation, we have m2 y double prime equal to negative k2 multiplied with y minus x plus k3y with initial conditions y at 0 equal to 0, y prime at 0 equal to 1, where the constants are m1, m2 equal to 1 and k1, k2, k3 equal to 1. To find the equation of xs, first we take Laplace on both sides like this. And then after we perform Laplace, we get the equation of m1 s2 xs minus x at 0 minus x prime 0 plus k1 xs minus k2ys plus k2xs equal to 0. And then we rearrange the equation in this form. After that, we substitute the initial condition as I mentioned before, and then we get the value of xs equal to ys minus 1 s squared plus 2. Moving on, finding the equation of ys using the second linear differential equation, we take Laplace on both sides. Performing Laplace transform, we get this equation. And then we substitute the initial condition. Finally, we get the value of ys equal to xs plus 1 over s squared plus 2. And then we perform simultaneous equation. First, we let xs equal to 1 and ys equal to 2. Then we get the value of xs equal to negative 1 over s squared plus 3. With the value of xs, we substitute into the equation of ys. And then we get the equation of ys equal to 1 over s squared plus 3. Finally, we perform inverse Laplace transform of the solution by referring to the table of Laplace transform. And then we get the value of xt equal to negative 1 sec 3 sine sec 3t. Lastly, we get the value of yt equal to 1 over sec 3 sine sec 3t.
How do you know that your answer is correct?
To answer your question, I'll pass that to our programmer.
Come here, let me show you. So, we use Maple software as a tool for reference to compare with our manual solution. We put the two systems in the software and then it will generate answer. So, this is the result. It has the same exact equation as we do manually. Therefore, we know our solution is correct. We also plot the graph through the software. This is how it looks like.
So what can you say about the graph?
We can see that this system has sinusoidal wave pattern for both positive and negative part. This pattern implies that the amplitude do not decay because the system has no damping. Overall, what can you say about this project?
Okay, overall, we achieve our aims. However, we would like to do some change in our project in the future. Okay, first, we would like to try to make the spring oscillates horizontally, and then we would like to observe the behavior of coupled pendulum when there is no spring in the system. I think that's all from us.
Okay, thank you for your interview. Bye.
Bye.
Come again. Come again.